Hello, today we're going to look at a pretty cool data structure known as a hash table. Now, I'm sure you're all very familiar with vectors, arrays, those contiguous blocks of memory. And the problem with those that we had was that when you're looking for an element, it takes O of n time. You have to look through the entire vector to find the element or to confirm that it's not there because, of course, you may not have looked at the element yet if you haven't searched through every single one. So, hash table. At its core, it's similar to a vector, but the magic comes with the hash function. And what that allows us to have is O of 1 lookup instead of O of n, which seems pretty insane at first, but it's pretty intuitive when we look behind the scenes. So, hash table. It starts pretty similar. It's going to be, in our case, we're going to look at open addressing, which I'll explain later. So again, we're going to have our same contiguous block of memory. And these hash tables in C++, it's like it's implemented as an unordered map. Python, it's like a dictionary, and we're gonna have key value pairs. And the key is what we put into the hash function to determine where it goes. The key value pairs can be any two data types. It can be an int to an int, a string to an int, which is a pretty common use case. And also, you can create your own classes, and that can be the data type in the hash table. But for our case, we're going to go string to an int, and we're going to look at like a name to an ID number in our hash table. So I guess we'll get started. We'll use for our name, we're going to use the name Aaron. So we have Aaron, and now to know where to store it in our array here, we're going to put it through our hash function. So Aaron goes into our hash function, and for now we're going to think of it as like some sort of black box, even though that's red, because we don't need the implementation right now. But essentially, it'll just compute some sort of pseudo-random number, so that the distribution of the keys will be more even, and with that number that we get, for example, x, we were going to mod by the size of our array. So we have 1, 2, 3, 4, 5, 6 elements. So mod 6 to get the index. In this case, that'll go to index 1, we'll say, just for whatever reason. We'll say it's equal to 1, and then we would put Aaron here. Aaron, let's say his ID is 14. So Aaron 14 goes in the index 1. Now we have our next string, we'll say it's Aaron. So here's kind of the important part of the hash function, is that similar keys, even if they're similar, they will not go necessarily to a similar location, which helps with spreading the keys out evenly. It gets a number z, mod 6 again, and now it gives us 5, index 5. So it goes all the way to the bottom, 0, 1, 2, 3, 4, 5. Aaron here, Aaron, and we'll say ID 25, okay? Now, if we wanted to find one of these elements, we would again go through our hash function, and we can ask the hash table, hey, is Aaron in the hash table, in the unordered map in C++? And so we ask the hash table. The hash table will do is compute its index using this hash function, and again it's a deterministic function, so we'll get the same output 1, index 1, and then it'll just look right away and it'll see Aaron is there, and that's the magic, because instead of looking through all the indices, we know that we have a deterministic index at the end, so we can just go right there. Now, given that there's only, given that we're going to mod 6, some number, of course there's going to be some collisions where we get the same index for different keys. So for example, we get a key Mikasa, put it into our hash function, it's going to give us another output. It can be, so here we had y, we had x, so we can get y now, and although it's different, we're going to mod 6, which caused the problem, and it could again hash the same one, because of course there are many more strings than there are finite number of memory we have here. So Mikasa is going to go to index 1. We put Mikasa in, but oh no, error is already there. So here is how the two strategies come into play. Instead we're doing open addressing, so instead of putting Mikasa there, we're just going to go to another space in memory. Now again, there's different implementations here. We're going to do linear probing here, so we just go to the next available memory address. And in this case, there's one available right here. We just put Mikasa right there. ID of 19. And the other one, separate chaining, would be if you had pointers in each of these locations to another bucket, and all the hashes that go here will go in the bucket. So Aaron and Mikasa would go there, but in our case, we're not doing that. And like I said, we're doing linear probing. There's also quadratic probing, where you go to the square of the next index to, or the hash function plus I squared, I being the number of times you've tried putting the value in the hash table. Okay, and you can see that after many iterations, you start to fill up this confined space. Let's say you had another value, Connie, and you had Armin, 11, 12, okay. When it starts to fill up, you'll notice that if we have to now look for Aaron again, we hash Aaron into our hash function, and eventually we'll get the same one again. But now when we go to, okay, Aaron's a bad example. Let's do Armin. Let's do Armin. We'll say Armin also collided at 1. And same with Connie. So when we put Connie in, we put it after Mikasa, and Armin went after Connie. So now looking for Armin, we go back to the top and we see, Aaron is there, but we're not done because we know that we might have to check the next address. So until the next address is not empty, we have to keep checking. So we go Aaron, Mikasa, Connie, and finally we see Armin here at index 1. And you notice that we're starting to get that O of n behavior. We're looking through a lot of the elements in the hash table. And this is where load balancing comes into play. For example, what we look at is a normal load balance would be like 5 or less, or sorry, 0.5 or less. So when 0.5, half your array is filled up, you're going to double the array. You're going to have to rehash. So maybe Armin ends up here now. And that allows you to then respread out the data. Yeah. And then in this case, we're gonna again rehash all the values once you double the size, and some of them might change because now we're modding. I said double, didn't I? We're modding by 12. All right, our mod 12, and so that'll spread out the values more. So yeah, those are hash tables. It's a pretty cool way to have O of 1 lookup with these pairs of values, and you don't have to have the pairs. You can just have a single int that you're hashing, and that's called a set. Same thing, but no pairs. And yeah, hope you enjoyed and learned something today. Thank you for your time. I'll see you later.